Good afternoon. Welcome to the lecture series of electromagnetic fields. Today the topic of discussion is uniform plane waves, and the topic what we are going to do is polarization today. So what is polarization? The time varying behavior of E vector at any given point in space is defined as polarization. So here we are going to study something about polarization, and we are going to derive the equation for polarization. Consider an electromagnetic wave which is traveling in the z direction. The E and H fields are assumed to be in the xy plane. So the E vector and H vector, they consist of two components, Ex and Ey, as well as Hx and Hy. So the electromagnetic wave or uniform plane wave which is traveling in this z direction and is varying in time will take up the equation of the form E equal to E naught into e power j omega t minus beta z. So as we have seen, the E vector consists of two components Ex and Ey. The E vector can be written as Ex Ax plus Ey into Ay. And assuming to the equation of uniform plane wave and at space z is equal to 0, E vector can be written as E equal to E1 into the real part of e power j omega t minus beta z. From the real part, E can be written as E equal to E1 into cos omega t into Ax plus E2 into cos omega t minus delta into Ay, where delta represents the phase difference between the x and the y components. So with this equation for uniform plane wave, now let us derive the condition for polarization, and from the condition let us talk about three types of polarizations: linear, ellipse and circular polarizations. So we will derive the condition for polarization, and from the previous equation we can write Ex to be equal to E1 into cos omega t and Ey equal to E2 into cos omega t minus delta. So we can say Ex divided by E1 is equal to cos omega t. So by squaring on both the sides, we will get Ex divided by E1 the whole square is equal to cos square omega t, which is equal to 1 minus sin square omega t. Or we can write sin square omega t is equal to 1 minus cos square omega t, which is equal to 1 minus Ex divided by E1 the whole square. Or taking away the square root, we will get the equation for sin omega t, where sin omega t is equal to square root of 1 minus Ex divided by E1 the whole square. Similarly, take up the second equation, which is Ey equal to, second part of the equation Ey is equal to E2 into cos of omega t minus delta. So expanding this in the form, Ey by E2 can be written as cos of omega t minus delta. So expanding in cos of A minus B formula, Ey by E2 can be written as cos omega t into cos delta plus sin omega t into sin delta, where cos of omega t is nothing but Ex divided by E1. So rewriting for cos of omega t, we can write this as Ex divided by E1 into cos delta plus, instead of sin omega t, we have this equation. So rewriting for sin omega t, we have 1 minus Ex divided by E1 the whole square into sin delta. So now we are going to rearrange this equation. So Ey divided by E2 minus Ex divided by E1 into cos delta is equal to 1 minus Ex by E1 the whole square into sin delta. So squaring on both the sides, we have Ey by E2 minus Ex by E1 into cos delta the whole square, which is equal to 1 minus Ex divided by E1 the whole square into sine square delta. So this is of the form a minus b the whole square. So expanding using a minus b whole square formula, we can rewrite this as Ey divided by E2 the whole square plus Ex by E1 the whole square into cos square delta minus 2 into Ey divided by E2 into Ex divided by E1 into cos delta. On the right hand side, we have 1 minus Ex divided by E1 the whole square, the whole bracket, into sine square delta. So we have to rearrange these equations. On the left hand side, we have Ex by E1 the whole square into cos square delta. On the right hand side, we have the same Ex by E1 the whole square into sine square delta. So bringing the sine square delta term on the right hand side, we can further simplify this equation. So for further simplification, Ex divided by E1 the whole square cos square delta plus sine square delta, and on the left hand side already one Ey by E2 the whole square is there. Therefore Ey divided by E2 the whole square minus this term remains as it is. So 2 into Ey divided by E2 into Ex divided by E1 into cos delta. On the right hand side, we have taken this term to the other side, so we have only remaining sine square delta on the right hand side. With this simplification, we know cos square delta plus sine square delta is equal to 1. So we can simplify this equation as Ex divided by E1 the whole square plus Ey divided by E2 the whole square minus 2 into Ey divided by E2 into Ex divided by E1 into cos delta is equal to sine square delta. So this is called the equation of polarization. So upon substituting the condition for polarization, let us derive linear, circular and elliptical polarizations. We will substitute the condition 1. The condition 1, that is, the phase difference delta is equal to 0. So we have to get actually linear polarization. Let us check whether the polarization is linear. So substitute delta equal to 0 in this equation. We have Ex divided by E1 the whole square plus Ey divided by E2 the whole square minus delta is equal to 0. So cos delta is 0, cos 0 is 1. So we have 2 into Ex by E1 into Ey divided by E2 is equal to, substituting delta equal to 0, we have sine 0. So sine 0 is 0, or else we can write this 1 minus cos square theta. So 1 minus cos 2 theta divided by 2, anyhow when we substitute you will get a value of 0. So let us have it as 0. So upon simplification we can see here a square plus b square minus 2ab. So this can be of the form a minus b the whole square. So this is Ex by E1 minus Ey by E2 the whole square. A minus b the whole square is equal to 0. Or else we can write this as Ex by E1 is equal to Ey divided by E2. Or from this we can say this as Ex is equal to E1 divided by E2 into Ey. So this equation is of the form y equal to mx, which is the equation of a straight line. Hence, the condition will give you a linear polarization. This proves the condition for linear polarization. So condition 1 has been proved for linear polarization. Next we will substitute condition 2 in the same equation. We will take up the equation. We will substitute condition 2. So what is condition 2? We will check up condition 2. So the condition is, second condition, let us take delta equal to some phase difference of pi by 2 radians. So upon substituting condition in this equation, we have Ex divided by E1 the whole square plus Ey divided by E2 the whole square. So cos 90. So this term will be 0 and which is equal to sin square pi by 2, which can be further simplified as 1 minus cos 2 theta divided by 2. So which is equal to 1 by 2 into 1 minus of minus 1, which is equal to 1. So we got the equation Ex divided by E1 the whole square plus Ey divided by E2 the whole square equal to 1. This represents equation for an ellipse. So with unequal amplitudes, this kind of wave represents an elliptical polarized wave. And we will move upon to condition 3, where Ex and Ey have equal amplitude and the phase difference delta is taken to be equal to pi by 2. So once again, substitute the condition in the equation of polarization. So we have Ex divided by E1 the whole square plus Ey divided by E2 the whole square equal to 1. We got, as in the previous case, as where we have the phase difference, we have kept it as pi by 2. The only difference is that there we have taken or considered the amplitude to be unequal. Now for the third condition, the amplitudes must be same. So we are regaining from the previous equation. So Ex by E1 the whole square plus Ey by E2 the whole square is equal to 1. So consider E1 and E2 to be equal to E0. As they are of equal amplitude, let E1 equal to E2 equal to E0. So our equation becomes Ex square plus Ey square is equal to E0 square. So this represents an equation of a circle. So a wave which is having the propagation of this type will have a circularly polarized wave. So this is how the condition for polarization is being proved for 3 conditions. Condition 1, which has equal or unequal amplitudes but the phase difference is 0, will give you linear polarization. Second condition, with unequal amplitudes with any phase difference, that will give you an elliptical polarization. And with condition 3, Ex and Ey have equal amplitudes and with phase difference exactly equal to pi by 2 will give you the equation of a circle. So with this we have come to the conclusion of this session. Thank you.